Hi, this is Marathonman. Today we're going to talk about the Figuera device, Part G, and the actions of Part G and the similarities to the, well, actually no similarities, the exact duplication of a Variac, just in a different form using DC. So let's get started. Hi, here we are in the test bed. This is a 100-volt power supply. It's fed by Variac, which we're going to discuss the differences and the similarities, exact similarities between a Variac and the Figuera active inductor controller. A Variac uses inductive reactance to control current flow. And what that does is they magnetically link to each other. Right now, there's almost zero flowing through it because of inductive reactance, which is the opposition to the current flow. Now, when you have current flowing through here and they magnetically link, that according to the Lenz's law, it will oppose the original current flow. But because you have AC alternating current, it's not the alternating current, the fact that it travels two different directions. That's totally inconsequential. The magic behind, the method behind the madness is that it's the rise and fall constantly that causes the inductive reactance and the Variac to work. Well, here we have the Figuera device that uses the exact same thing, inductive reactance, to control current flow. What it does is increases and decreases the circuit on both sides. You have the brush rotation that's increasing and decreasing the circuit. And according to Faraday, any increase and decrease in the circuit, in the magnetic field, in the current will create an EMF. As you add windings to the circuit, you're increasing the flux for that circuit, which is, according to the Lenz's law, the opposition to the original current flow, any EMF created. So the similarities between this and this are exactly the same. According to inductive reactance, any current change falls under inductive reactance. So we have, in fact, current running through this. And as you add windings and subtract windings, you're increasing and decreasing the amount of flux associated with this circuit. So therefore, you're able to give DC frequency, which then falls under inductive reactance, which is the opposition to the original current flow. So these two items are exactly the same. One uses AC, one uses DC. This one has a fluctuating current. This one does not have fluctuating current. It has a fluctuating circuit. So if you increase and decrease the circuit, you will have opposition to the original current flow. So now, let's get started and actually see the lights dim and increase and decrease in unison. Okay, so now we're going to turn this Variac on, and we're going to, unfortunately I can only put about 75 in here because the way I built the circuit, mistake on my part. So I have a meter here that tells me just how many volts. I have the 12 volt on the same circuit, so I can only do too much. I like this power supply because I can control everything through the AC Variac that uses inductive reactance, as does the Figuera device. So, let me adjust this camera just slightly. Yes, I'm by myself, so it's a pain in the ass, and I'm using my phone to record this. So we have a certain amount of voltage and amperage coming through here. We have the negative flowing through the light bulbs on both sides of the Variac to the positive brush. Now, let's vary this. Now, do you see that? We have both of them in complete unison, one increasing and one decreasing in current flow. And if you slow this video down, you will see that each one is in complete unison. That is an active inductor controller controlling DC current flow using inductive reactance all day long. So, if these were my primaries here, let me move the camera again. So we have our primaries right here with our secondary in between. What we're doing, what Clemente Figuera did, was he powered the device up. So you have two opposing electromagnets. And in order to get movement into the secondary, you had to reduce one and increase the other. Once you polarize the secondaries and current begins to flow, according to the Lenz's law, a second field will form. It's that field that is sandwiched in between the two primaries. When you reduce one to get the sweeping action, you're actually creating an electric field. The increasing one is shoving that opposing field across that electric field. This gives the illusion of motion. It's motion, it's virtual motion, but it's still motion according to the laws of physics, our universe. Sure, your standard physics that are taught in the colleges, they won't teach you this. Of course not. The powers that be control all education. People should realize this by now. So, these two electromagnets, side by side, are exactly the same. They have the same spin direction, right? So, these are north face opposing electromagnets. But when you put them on end, you have one electromagnet with a magnetic field spinning in this direction, and you have one spinning in the opposite direction. So, therefore, you're fulfilling the exact same requirements as a 4-pole generator using only 2 poles. So, the magnetic fields will never, ever change direction. They are opposing at all times. But when you decrease one and increase the other, they're both combined electric field. Meaning this one's increasing, the induced is in this direction. This one decreasing, the induced is in this direction to try to maintain the field. See what I mean? So then when you increase this one and reduce this one, the fields are in the opposite direction. So you're fulfilling the same AC requirements as a standard 4-pole generator in a stationary scenario. So let's go to some of the graphs that I have, and I will explain this further. Here we have one of my graphs. This is the original patent, 1908 patent. They show R as resistance. Never do they say this is a resistor in the patent. Why would a physics professor build a device that has a heat death resistor. They're not. He wasn't. So what this shows is there's this much resistance at this contact point. There's this much resistance at this contact point. You get my drift? And then each tiny wire is just to show you that this line has so much resistance. These two somehow are connected. They have the same amount of resistance depicted here. Excuse me. But you get the point. These squiggly lines don't exist. What these are actual lengths, loops of wire looped around a core, and it depicts this much resistance. They show this, he describes it in the patent as resistance, and it's drawn in its elementary manner to facilitate the comprehension of the device only. R does not exist. It never has, it never will. It's an inductive reactor it's an active inductor controller using inductive reactance to control current flow. And another thing I want to talk about is the charge separation. The charge separation that it shows in the patent, not in the 1908, but the before patent. He's stupid and he's not stupid, but he was greedy and he tried to repatent everything. But anyways, they show that charge separation. In the patent, he talks about a commutator. If you wanted, a commutator is in the system, and it's on the same shaft as the motor. So he turns AC into DC on the secondary feedback to power the device. That is the feedback. Now, another thing I want to talk about is the ratio of the cores. Clemente Figuera showed a core, and the primaries are twice as big. Measure these, they are twice as big. So that led me on the path of a 2-to-1 ratio, which so far it's been correct. Also, you've noticed, let me get in close, there's a gap in between each one. This gap is there for a reason. When I was working with a researcher in the past, we were doing studies and exchanging information. When the field lines were compressed and then swept back and forth, when it was leaving when they were butted up against each other, when it left this core and entered the other one, there was a peak, a dip, and another peak. Why? Because the field left this secondary core and went in to the primary core. That caused an additional peak. Well, that's the reason why the gap is there, because in order to get the inductive roll-off in the secondary output, the waveform, you have to have a gap. That way it just pushes it just past and then back to the other side. That's all you're doing is pushing from gap to gap. Now, some people will argue and blah, blah, blah. I've heard all this crap from EF and OU and all over in the past years, and I'm not going to go through it. It's plain and simple. That gap is there for a reason. R does not exist. This is an inductive reactor, an active inductor controller. Okay? And as I've shown you here, this is the inductive reactor. It uses the red, or the green, is the induced current. The primary current flow in red flows through, and because you're magnetically linking to the circuit, you're increasing the magnetic field for that side. And it just so happens, because it was created within the circuit, according to the Lenz law, it will oppose what created it. So as you move the brush and increase for this side, you're increasing the inductive reactance. You're decreasing it from this side. Okay? So on this graph, when you compress the field lines, you cause a bulging effect. And this is the reason why I explained that you can have a larger secondary to take advantage of this field. Now, this was downloaded from a very reputable magnet manufacturer. They have since took it down, probably because of me, probably not because of me, I don't care. But this depicts the magnetic field being compressed, the field lines compressed to match that of a standard north-south generator, rotating generator. And these field lines compress and bulge out. So that means you can have a larger secondary to take advantage of this field. So when you are increasing the side of a Clemente Figuera, you primaries and your part G does not have mutual inductance. Since they are not on the same core, it's this plus this. That means these two added is going to be that much of a voltage drop because you're storing into the magnetic field. You may be decreasing the circuit, but you're storing it this way. You're storing into the magnetic field. When you increase the current, you are storing into the magnetic field. Now, on the reducing side of the Figuera device, remember, there's part G, there's set N and set S, and you're splitting the inductor in two. So that means you basically have two halves. On the reducing side, when you increase the current, you increase the opposition to the original current flow. So that means you're releasing potential into the system. So that means it's L1 plus L2, meaning half of the inductor is releasing potential into the system and half of part G, one of the sets, are releasing potential into the system. These two combined offset the rising side, storing into the magnetic field. Remember, there's going to be a voltage drop. There's a voltage release, voltage increase here, and a voltage decrease here. So this side offsets this side. And here we have another one of my graphs. This is the northern semicircle, the upper semicircle. This is the lower semicircle. When you have the brush travel, as it's depicted here, and it's traveling this direction, set S is decreasing. It's releasing its potential into the system because you're increasing the opposition, lowering the current. So it's releasing its stored potential into the system. On set N is increasing its current flow. It's storing into the magnetic field. So as we rise up to the northern upper semicircle, set N would be releasing its potential. Set N is decreasing, releasing that stored potential into the system, and set S is increasing in current flow because you're shrinking the circuit. It's storing into the magnetic field. So what you're doing between this action is you're sweeping the current back and forth between the two primaries. What you will have, since current is flowing in to set N and set S, everybody knows that current flows from negative to positive, at least I hope you do. Ben Franklin had a 50-50 chance of getting it right, and guess what? He was wrong. Current flows from negative to positive. Why do you think you have such a fat ground line on everything? So as the current flows in here to the positive brush, you will have two NN fields, opposing fields, that split the inductor in two. Therefore, you're able to split this feed into two, and you're able to control the current flow of two separate feeds 180 degrees from each other in complete unison. Now, Clemente Figuera didn't show all this core in the patent. The only thing he showed was the actual brush rotation, and he showed that there is some kind of resistance at these specific points. This is exactly what he was talking about, an active inductor controller. Now, as it spins, and I've already shown you, and I'll show you again, it uses inductive reactance to control current flow. So, I hope everybody has learned something from this, that Clemente Figuera did not use a resistor or resistor network. He used inductive reactance to control current flow. And what he did was he took an active inductor controller giving DC frequency through the use of inductive reactance. He increased the circuit, which increased the opposition to current flow, creating EMF that opposed the original current flow, what created it. So therefore, the current reduces. Well, when you shrink the circuit, the current rises again. So therefore, you just gave current, DC current, frequency. Of course, you know that the inductor opposes all AC current flow, but it lets DC pass. So what you have is a very, very orderly rise and fall of current flow of two different DC feeds in complete and utter unison. And let me show you one more time. This is inductive reactance all day long. Clemente Figuera used an active inductor controller to control current flow in his device, not resistors. So what he did was he's compressing the field lines to match that of a standard high-intensity north-south field, a standard generator. He's reducing 1/3 to 1/2 to get the sweeping action. No more than a half, because you don't want to lose that compression. Since you have both of them that are compressing the field lines to match that of high intensity, this one's in charge of half, this one's in charge of the other half. But when you reduce it 1/3 to get the sweeping action, you're divide that by 2, and you're actually reducing it by 1/6. So if you reduce it by 1/6, it takes 14.8 pounds per square inch to produce 1 kilowatt. So if you're reducing it by 1/3, you're reducing it to like 12.2 psi, pounds per square inch. 12.2 psi is not 14.8, so you're not creating your kilowatt. You actually are producing less than a kilowatt. That's where the secondary feedback comes into play. You're adding that extra potential into the system, increasing the voltage in the line. It's called forward biasing. When this side is reducing, the primary half, the one set of electromagnets, half of part G, and the secondary feedback forward bias the rising side. It increases the voltage, which allows more current to flow to replace that reducing half or reducing sixth. It maintains the pressure throughout the entire sweeping action. And it circulates that power through the system. You have an exciting side and you have a power output. Those are two separate systems, just happen to working together. Since they're opposing, it's not like a transformer that everybody thinks. It's not when you put a load on here, it's not doesn't directly tax the input because it's a separate system. Since they're all opposing, you're catching that on the reducing side. You're generating off the reducing side, but you're still keeping it 14.8 pounds per square inch by all the feedback. and the forward biasing. So you keep that field compression and you're going back and forth in the gap. That causes, once you go past that into there, and as this comes on that last winding, you'll notice that the brush will stay on that last winding for quite a while. The original Clemente Figuera inductor controller was an EI, more than likely was an EI core. And that was created, the Variac was created by Adi of Zeiss. So, and he was in Germany. He sent his stuff off to be manufactured in Germany. So there's only two people at the time that can do it. It's either Zeiss or Otto. And who would you go to that created the Variac in the first place? Duh. Pretty simple, Zeiss. So his original core was more than likely just a straight core. That was a closed core. You need to preserve the magnetic field. So it was an active inductor controller that controlled the current flow, compressing the field lines, and then you're reducing one, increasing the other to get the sweeping action. Then you have some feedback coming in, just like Clemente Figuera said, to power the motor and to self-sustain. And I want to appreciate you people that watched the video, and I hope you learned something, I enjoyed making it, and I'm finally making some progress. As you see, I've lost a massive amount of weight. I've lost 40 pounds. I live on a farm now, so I eat very healthy, and unfortunately my time is taken up with the farm and my garden, acre garden, and lots of good things. So my time is very valuable and limited, but I am slowly moving to a working device, and I will get there soon. When, I'm not sure, but I will get there. So keep wearing, get out there, do the research, verify everything that I just told you. Do it for yourself, improve your knowledge, and let's work together and strive to get these devices running, get them out there, and get away from the very, very wasteful natural resources that are we're on a present downhill slide into a hole of oblivion. So let's work together, people. Let's increase humanity. Thank you.